So before we begin the more difficult section of this unit, I want to ask you a question which I think all of you will know, and it relates to this unit, so keep that in mind. The question is, how much is a dozen of something? And I'm sure that all of you know that a dozen means 12, right? 12 of something. You can have a dozen eggs, and here's a picture of a dozen eggs. You can have a dozen roses. My favorite, you can have a dozen donuts if you go to the appropriate shop. And then dozens can come in different types, right? You can have a dozen of the white eggs, you can have a dozen of the brown eggs. Dozen just means 12 of something. Um, so that's what a dozen means. The next question, again, I'm sure you can answer. How much is 2 dozen of something? And again, I'm sure you know that 2 dozen of something is 24 things. So you can have 2 dozen eggs, that just means 24 eggs. You can have 2 dozen roses, again, that just means 24 roses. Or you can have 2 dozen donuts. Again, it just means 24 of that thing. Now, why does it mean 24 of that thing? Why does 2 dozen mean that? And again, what you're doing in your head is you're saying, look, 2 dozen is 24 because 1 dozen is 12 and 2 times 12 is 24. So that's how much 2 dozen is. So that's sort of the calculation that you're probably doing in your head when someone says, I bought 2 dozen eggs or something like that. The other question is, how do you know what a dozen means? How do you actually, when did you learn that a dozen meant 12 of something? For most of us, I imagine that where we learned that was sometime in grade school, possibly even earlier. But at some point in your life, someone told you a dozen meant 12 of something. And maybe that seemed strange to you at the very beginning when you were told that, but eventually you got used to that idea that dozen was just another word for 12 of something. And eventually, because you were exposed to it so much, you became used to the fact that the word dozen means 12 of something. So that, again, all of what I'm talking about might not be earth-shattering to you, but I want you to keep in mind the concept of what a dozen means as we move forward. Okay, the rest of this section basically deals with counting and weighing atoms when you're dealing with materials. Can you actually count how many atoms or molecules there are? And relating that to how much the atoms weigh. So that's basically what we're going to talk about for the rest of the unit. So the first, I'm going to ask a series of questions. I'm calling it Let's Play How Much Does It Weigh? We have the information for hydrogen here. You can see hydrogen has an atomic number of 1. That means all hydrogens have 1 proton. This is the average atomic mass of hydrogen. So what that means is your average hydrogen weighs 1.0079 atomic mass units, or if you want, 1.0079 Daltons. So if I showed you one hydrogen atom, and here's one typical hydrogen atom, and I asked you how much it weighs, you would basically count up the protons and neutrons and tell me the information, or you would tell me the mass of this hydrogen atom in Daltons. Well, this thing has 1 proton, so its mass, or if you want to call it weight, its weight is 1 Dalton. Now, if I had 2 hydrogen atoms, like this, how much do they weigh altogether? Again, I'll pause for a second and have you think about that. And the answer is that these 2 hydrogen atoms together, taken as a group, weigh 2 Daltons because each one has 1 proton. Then we can do the same. Another question that I'd like to ask is, if it were possible to have individual hydrogen atoms, and I will admit that it's not very easy to do this, but imagine that you had 1 hydrogen atom. Could you actually weigh that on a scale that you might have in your house, or maybe even a fancier scale like the one you got in your lab kit? Could you do that? The answer is no. It weighs too little to actually weigh out on something that you might have in your house. The same is true if you had 2 hydrogen atoms. Same is also true if you had 3 hydrogen atoms. If you had 3 of them, because of what we've discussed in past units, you know that 3 hydrogen atoms like this weigh about 3 Daltons. But in real life, you couldn't actually figure that out. You have to basically take my word for that. So you can't have 3 hydrogen atoms and and be able to weigh them out on a conventional type of scale that we might have lying around the house, or even one of the relatively fancy scales that we might have in a lab. Because 3 hydrogen atoms are just too little, they're too light to be able to register on a scale. Here's a slightly different question. What if you had 1 billion hydrogen atoms? Would you be able to weigh that out on a scale that you might have at home or a scale that you might have in the lab? The answer to this is no. I don't expect you to know that just by me asking you the question, but even if you have 1 billion hydrogen atoms, and 1 billion can be written as 1 times 10 to the ninth, even if you had this many, they still weigh too little to register on a scale. And we'll sort of develop the reasons for why that is in the next bunch of slides. So because you can't weigh 1 billion hydrogen atoms out on a scale, you can ask yourself the question, how many hydrogen atoms or how many atoms do you actually need to have before you're able to weigh them out on anything remotely approximating a conventional scale? So I want to keep this information about hydrogen over here as we answer this question. How many atoms do you actually need before you're able to weigh them out, before they weigh enough to weigh out? It turns out that you need about 1 times 10 to the 23 atoms. And again, this is a little bit of a weird number. This is the largest reason as to why we brought up scientific notation in the earlier units, because we're going to have to deal with numbers that are this large going forward. 1 times 10 to the 23, written out in the more conventional way, is this. It's 1 with 23 zeros. That's a lot of zeros. That's a lot of atoms that you need to have before you're able to weigh them out, before they weigh enough to register on a conventional scale. Now, it doesn't have to be exactly 1 times 10 to the 23. It can be a little bit less, it can be a little bit more, and it depends on the atom. But this is roughly the area, this is roughly the number of atoms that you need before you're able to weigh them out on a scale. So another thing that I want to point out to you is that historically this was done backwards. In other words, chemists were weighing out different chemicals and for a long time, and they would weigh out a certain amount, enough that would register on a scale, and the question over time arose, how many atoms or how many molecules am I actually weighing out when I scoop up a bunch of chemicals? How many are there? We're doing it in the reverse form. I'm basically telling you in the previous slides that 1 hydrogen atom weighs about 1 Dalton, and it turns out that you need 1 times 10 to the 23 of the atoms before they weigh enough to weigh on a scale. Historically, it was done in the reverse way. People weighed stuff out, and then later, after the fact, they actually tried to figure out how many atoms they were scooping out of a little bucket of chemicals or something like that. So just for historical purposes, keep that in mind. The other thing is that this number, 1 times 10 to the 23, I'm going to change it in a minute, but coming up and figuring out how many atoms someone was actually scooping out and putting on a scale took many, many years, and probably actually hundreds of years to figure out. So this was not a trivial thing to actually figure out. So the reality is that 1 times 10 to the 23 hydrogen atoms weighs something, but the chemists at the time wanted to relate how many atoms they were actually scooping out and weighing on a scale. They wanted to relate that back to some of the information that was actually on the periodic table. And I told you here that 1.0079 in the case of hydrogen means that the average hydrogen atom, one single atom, weighs 1.0079 Daltons. And the chemists at the time, when they were figuring this stuff out, how many atoms am I scooping out, they actually tried to relate how many atoms they were scooping out back to the average atomic mass of each atom. And it turns out that basically what they said is, look, this means 1.0079 Daltons, but what if it actually meant 1.0079 grams? For those of you who aren't super familiar with grams, gram weighs about as much as a paperclip, or your average paperclip weighs about 1 gram. And you can weigh a paperclip out on a scale. So basically, the chemists then asked, why don't we reuse this number? And sometimes it can mean 1.0079 Daltons when we're talking about the weight of a single hydrogen atom. But why don't we switch the units under different circumstances and call it 1.0079 grams? If this is 1.0, if we have 1.0079 grams of hydrogen atoms. How much do they weigh? And it turns out that it's a very specific number. It turns out that 1.0079 grams of hydrogen atoms is 6.02 times 10 to the 23 hydrogen atoms. This is how many hydrogen atoms it takes to weigh 1.0079 grams. And again, this you can weigh out about 1 gram worth of things on a conventional scale. So the idea is that when scooping out a certain chemical, let's pretend that you could scoop out hydrogen atoms. If you scooped out this many grams of hydrogen atoms, in other words, if you scooped out a paper clip's worth of hydrogen atoms, um, it would contain this many hydrogen atoms. If you could actually count up all the hydrogen atoms, there would be this many, which is about 6 times more than this number, but it's in the same neighborhood. This is the number that's used over and over again in chemistry when counting atoms and molecules, 6.02 times 10 to the 23rd. And again, you're going to have to become accustomed to entering this number into your calculator because your calculator most likely will not have the space for punching in all of the zeros in this type of number. You're going to have to punch this in using scientific notation. So this number is used over and over again in chemistry. It actually has a special name. It actually has 2 special names. Sometimes it's called a mole or 1 mole. And again, I'm not talking about the furry creature that burrows under your lawn. 1 mole is just another way of saying this many things. In the same way that 1 dozen is just another way of saying 12 things. So because this is a little bit of a pain to say, and to write out on the board, chemists have come up with a different name for it, a shorthand word for it, and that is a mole or 1 mole. So 1 mole of something is just another way of saying 6.02 times 10 to the 23 things. The number 6.02 times 10 to the 23 also has a different name. Sometimes people will refer to the number itself as Avogadro's number, and that's just Avogadro's number is just another way of saying 6.02 times 10 to the 23. So Avogadro was a famous chemist who lived a long time ago. He actually didn't figure this number out, but they named it in honor of him anyway because he did other relatively famous chemistry things. So just to summarize this, I want you to realize that 1 mole is, when I say a mole or 1 mole, I am just saying 6.02 times 10 to the 23 of whatever it is that I'm talking about. And sometimes people will say Avogadro's number in place of this huge number. So I want to talk about something else now. On a couple of slides back, we were talking about how much does 1 hydrogen atom weigh. It weighs about 1 Dalton. If you have 2 hydrogen atoms, they weigh about 2 Daltons. If you have 3 hydrogen atoms, they weigh about 3. Let's talk about helium for a second now. Helium has an average atomic mass of roughly 4, I'm going to forget the decimal places here, but it has an average atomic mass of about 4 Daltons. So if you had 1 helium atom, it would weigh about 4 times as much as 1 hydrogen atom. Hopefully you can see that. You can see the 2 neutrons and the 2 protons making this atom weigh 4 Daltons, compared to this one which just weighs 1. So this guy weighs 4 times as much as the hydrogen atom. Then, if you have 2 helium atoms, altogether they weigh 8 Daltons. 8 Daltons. If you have 2 hydrogen atoms, altogether they weigh 2 Daltons. So 2 helium atoms weigh 4 times as much as 2 hydrogen atoms. And you can play this game on and on and on. If we have 3 helium atoms, altogether they weigh 12 Daltons. If you have 3 hydrogen atoms, altogether they weigh 3 Daltons. And again, 3 helium atoms weigh 4 times as much as 3 hydrogen atoms. So one of the punchlines is that you can figure out the relative weights of the atoms just by looking at the periodic table. In other words, I don't need to show you these cartoons necessarily. You can just look at the periodic table, read this number, and compare it to a different atom. And you can say, look, helium atoms weigh about 4 times as much as hydrogen atoms. The other punchline is shown on the next slide. So on the previous slide, we just said that your average helium atom weighs 4 times as much as your average hydrogen atom. And I want to bring you through this a little more slowly. So your average helium atom weighs 4 times more than your average hydrogen atom. And again, on the previous slide, we basically said, look, if that's true, then two helium atoms weigh about 4 times more than two hydrogen atoms, right? And then we extended that even further. We said, look, if you had 100 helium atoms, those 100 helium atoms taken as a group would weigh 4 times as much as 100 hydrogen atoms taken as a group. And you can extend that even farther. You can say, look, if you had 1 billion helium atoms, those 1 billion helium atoms would weigh 4 times as much as 1 billion hydrogen atoms. Because all of the above is true, it's also true that if you had 6.02 times 10 to the 23 helium atoms, those helium atoms taken as a group must weigh 4 times as much as the same number of hydrogen atoms. And here I'm using Avogadro's number, or 1 mole of helium atoms and 1 mole of hydrogen atoms, for a very specific reason. So if you have this many helium atoms, they have to weigh 4 times as much as the same number of hydrogen atoms, for the same reasons that we were discussing above. So now, if I asked you specifically, how much does 6.02 times 10 to the 23 helium atoms actually weigh in grams, let's say, what's the answer? You can pause here and think about it. It might be obvious to some of you. It might not be so obvious to others of you. This sometimes is a little bit of a difficult concept. So you can pause here. The answer is that 6.02 times 10 to the 23 helium atoms turns out to weigh 4.0026 grams, the same number as you see in the periodic table for helium. Why is that true? Why? Again, you can pause to think about it. If it was difficult for you to come up with that answer, or if you didn't know what the answer was, it might help to pause for a second and think about it, and I'll try to explain why that is now. The reason is, on the previous slide, or one of the previous slides, we said that 6.02 times 10 to the 23 hydrogen atoms weighs 1.0079 grams. That's how much that many hydrogen atoms weighs in grams. But we said that each helium atom weighs about 4 times as much. So if you have the same number of helium atoms, it's going to weigh 4 times as much as this many grams, which turns out to be about this many grams, 4.0026 grams. So because we know each helium weighs 4 times as much as each hydrogen, then you know that if you have 1 mole of helium atoms, it has to weigh about 4 times as much as 1 mole of hydrogen atoms. And we already said that 1 mole of hydrogen atoms weighs 1 gram. So this is actually a little bit of a deep result. And I'm just sort of showing those bullet points again. But the deep result is that you can now figure out how much 6.02 times 10 to the 23 atoms of any type of atoms, how much they weigh, just by looking at the periodic table. So 1 mole of hydrogen atoms weighs this many grams, weighs about 1 gram. 1 mole of helium atoms weighs about this many grams. But you can do this for any of the elements in the periodic table. You can look at boron and you can say, look, if I have 10 grams or 10.8 grams of boron, that actually turns out to be 6.02 times 10 to the 23 boron atoms. You can do it in reverse. You can say, look, if I have 6.02 times 10 to the 23 carbon atoms, how much does it weigh? Well, it turns out that it weighs about 12.011 grams. And you can do this in either direction. You can say, if I had 14 grams of nitrogen, how many nitrogen atoms do I have? Turns out I have this many. I have 1 mole of nitrogen atoms, 6.02 times 10 to the 23. Or you can ask it in reverse. You can say, if I have 6.02 times 10 to the 23 oxygen atoms in this case, how much do they weigh altogether? It turns out that they weigh about 15.999 grams. So this is a little bit of a deep result. It may be confusing to you. If it's confusing, you might want to replay this or consult your book or email me. But that tends to be the most, one of the more difficult portions of this unit, and the rest of the time is going to be spent sort of trying to familiarize you with these concepts by asking you a series of questions and sort of just getting you accustomed to thinking about what this number is, about calling it a mole, about converting it into grams, that type of thing. So that's what the rest of this unit is about.